that it can access. And we can specify that policy in code. So since we're implementing XML HTTP request as a JavaScript object, our URL policy is now also a JavaScript function, maybe mapping URLs to URLs. Then there's complex APIs like document. Document is used by almost all web applications to update interfaces dynamically. If we didn't allow access to a lot of that, we'd break almost all the legacy applications out there. But it is a very rich API. There's lots of different node types, form nodes and script nodes, each with their own properties. And we want to allow access to some. So we might want to allow access to getElement by ID. We might want to reinterpret assignments to inner HTML to filter the HTML before it actually makes it into the browser. And we might want to deny access to browser-specific extensions until we understand the security consequences of those. And so we do this by membraning. A membrane is just an object that wraps an object graph. So when the untrusted code is dealing with, for example, a form node, what it's really dealing with is our implementation of form node, and that implementation of form node delegates an awful lot of its operations to the real form node, but the membrane stands in between the third-party code and the real document so that it can, for example, rewrite the argument to setting inner HTML. And then location, we also membrane, but for different reasons. So location is a very simple API. It's a string. You can access parts of it or you can set it. But when you're setting it, you're dealing with it's a uniform interface, but to do very different kinds of authority. So when you set the location and the new URL only differs from the old URL by the fragment, then you're navigating within the page. You're changing the position of the scroll bar. Otherwise, you're replacing the current document with a new document. We may want to allow untrusted code to navigate within the page, but we may want to disallow them from changing the current document, or we may want to reinterpret that. And having a membrane in between lets us do that.
So that's the security policy. That's how you specify a security policy. How does that security policy fit in with the entire pipeline? Well, when a user accesses some social networking site, they visit a container. In this particular case, the example container is container.com. The browser sends a request to the social networking site. That in turn sends that request on to the cajoler. Now, the cajoler is our code rewriter for Caja. It rewrites the code to make it safe. It first passes that request on to fetch the particular gadget. So this is the third-party code that is fetching from gadget.com. And what is a gadget? Well, a gadget is just a web application. It consists of some HTML, some CSS, and some JavaScript. By virtue of being essentially a virtual browser, the cajoler fetches the HTML page. It follows any script source links. It follows any style sheets that are being included. It fetches them, it analyzes them, and it rewrites them to be safe. And by safe, I mean it applies the particular security policy that the container has chosen. And it returns that safe piece of HTML and that safe piece of JavaScript back to the container. Now, the important point to notice here is that the security policy that is being enforced here was chosen by the container. And so if the container finds new threats when it chooses to adapt its security policy, it's able to do that by passing new rules on to the cajoler. The security policy consists of some static pieces which are reflected in the safe HTML and some dynamic pieces which are reflected in the safe JavaScript. The container collects several such cajoled pieces of code. It wraps it in its own Chrome, and it returns that to the end user, and that piece of code ends up being displayed. Now, how does a particular piece of gadget look like once it's cajoled? Well, here's a sample gadget hosted on gadget.com. It consists of some HTML, which references some CSS. It has a hello world, which is clickable, and when you click it, it causes a little alert box to pop up. You'll notice that in this particular case, the user has decided that the B tag shouldn't mean bold anymore for whatever reason. It should mean the color blue, and that's fine, I guess. What happens is the cajoler takes all of that content, it analyzes it, and it produces the two blobs of text that I was mentioning earlier. So it produces some static HTML code. Things to notice in the static HTML code is the introduction of a cajoler-generated ID. In this case, it's gadget123, and that scopes the style rule to be only applicable to this particular gadget. In particular, this style rule does not apply to the container, and it does not interfere with style rules that occur in other gadgets. You'll notice that there is an ID that is applied that allows the JavaScript, when it finally executes, to add back the event handlers that were removed originally. In the JavaScript portion, here's the dynamic portion of the security policy being applied. The alert function that is used is actually fetched from the container. So the container passes this G triple underbar, which contains the alert object, which it is granting to this piece of code. Now that alert object could be the raw alert, which could be the original alert function. If the container decides that this gadget should be able to call alert, it's safe for it to call alert. Alternatively, it may be some attenuated version of alert, for instance, a throttled version that only allows the gadget to call alert 10 times or something to prevent the gadget from overwhelming the user. And you'll notice that the actual function remains pretty much the same. Finally, this code is put together and returned to the container. The container sends kahita.js, which is object capabilities for JavaScript. It is the core piece of Taha. It includes demeter.js, which is our implementation of the virtualization for the DOM. It includes the container HTML, which the container uses to chrome all of its content. And then it includes each of the cajoled pieces composed by the container. Now, one thing to notice here is that the cajoler returns the static HTML and the JavaScript separately, which means that the container can display all of the HTML immediately, and for latency reasons or for security reasons, only cause the associated JavaScript to execute later, perhaps on user interaction. And that's the page that gets served up to the end user.
So the first problem that we discussed was the policy that's implemented in the browser might not be what you want. So if you ever find that you can't wait for new standards to make it through committee and be implemented by browsers, or you can't wait for browsers to fix a security issue that is critical for your users, but maybe not highest priority for the web at large, or you can't wait for a large group of third-party developers to rewrite their code, then you need your security policy in code that you control.
The second problem that we remember we had was that the security policy that you come up with may evolve over time because the threat model changes over time. Now, we don't have a silver bullet here. We still require you to do security up front, to do security design up front, but you may get it wrong. And you may get it wrong for a variety of different reasons. The cost of an exploit may change. It may decrease over time. The cost of weaponizing an exploit may decrease. The amount of data that you hold as a social networking site may increase, making you a more attractive target. Or you may just have overlooked an attack vector, or a new attack vector arises. For all of these cases, you need to be quick to respond to new threats as they arise. And in order for you to be responsive, you need to have your security policy in code that you control.
And the way to get your security policy in code that you control while still supporting legacy code is by virtualization. The methods that I discussed earlier, power boxes and proxies and membranes, all of these are tools that you need in your toolbox.
So what we set out to show you was, well, in our particular example, we set out to exemplify this in terms of social networking sites. But for whatever problems you face, you may realize in circumstances where you're not able to predict the security model that needs to be applied in the long run, and where you're accumulating legacy APIs, where you're accumulating legacy code, you need virtualization in order to be able to respond to threats as they change.
So these techniques are what allow you to keep legacy code running. It's still running against what it thinks are the same old APIs, the same semantics, but suddenly the actual amount of authority it has is bounded. So the network is filtered by code. The portions of the DOM under Caja that it can access are specified in the container HTML. And all of this stuff, rolling out a new security policy is now just a software update.
So this is not all theoretical. We actually, as we say, implemented software virtualization in our project Caja. It's an open source project. Feel free to find out more about virtualization in general and virtualization of the DOM on our project page. You can contact us. And you can try out using a variety of different security policies by visiting caja.appspot.com. Thank you.
Are there any questions?
John?
Caja has actually been on my to-check-out list ever since I met you guys for the last years. But I don't know how much time I need to allocate my spare time or whatever to really dig into this.
I think you should allocate all your spare time to our project. so the question was, how much time should you allocate to exploring Caja? And I think the techniques that we're describing here, how to do virtualization is applicable to a lot more than just Caja. It's not just applicable to the same origin domain. So I think learning about Caja, in as much as it helps you in other aspects of your security work, is valuable. And it's especially valuable when you've got a legacy code problem and you need to be able to kind of come up with security policies, and you're wondering, if only I could write some code, if only I could get a little bit of code in between me and the hard iron.
And specifically for, specifically for Caja, specifically for the browser, if you're doing virtualization completely, then as an end user, you really have, there's really no or a very small amount of learning involved, because you're essentially using the same APIs, the same language that you're used to already. Now, the extent to which Caja is able to provide you with that it varies depending on whether you're looking at our CSS emulation, our JavaScript emulation, or our DOM emulation. But the solution with virtualization means that your end users, your end developers, don't really have to think about this particular problem very much at all. Glad.
I'm wondering about the extent of virtualization. Basically, if there are browser quirks that allow, for example, the window object to be leaked to separate function, would that mean that the virtualized DOM window would be leaked, or would it be possible to access the actual window object?
So the question is, depending on how much virtualization is being done, is enough virtualization being done that when is it JavaScript language features or DOM features result in the window object leaking? Is it the real window object that leaks, or the virtualized window object? Is that an accurate summary of the question? So there is a distinction between the language, what the language ends up leaking, and what the DOM ends up leaking. The JavaScript that we use, that we virtualize, is a subset of the complete JavaScript language. We use the object capability subset of JavaScript, which allows us to prevent the kinds of leaks that you talk about.
So there's one thing to note, though, is that there's this chain of requests, and that comes with certain context. So we have a very good idea when we're cajoling code, what is